Alright, so we have talked a little bit about the boot process, and one of the things that kept coming up over there was this concept of virtual memory, right? So it's worth spending a little bit of time trying to understand virtual memory in a little bit more detail. Again, something that I have talked about a little bit in the past, but it's a complicated enough area that it's worth revisiting. So first of all, why virtual memory? This is sort of just a quick recap of the view of the world that different programs see, right? Let's say that I have two processes. Once again, I'm jumping ahead and saying that I've already got a booted Linux system and so on. But in general, what happens is, let's say that I have two processes. There is this process A and there's process B. The interesting thing is both of them sort of have a very similar view of what memory looks like. Okay, what I mean by that is, I could, for example, give both of them full access to a range of addresses starting all the way from 0 up to the full 32-bit FFFF, right? Now what that means is, as far as process A is concerned, technically it has access to a 32-bit address space, which means that potentially it could try and access anything up to 4 GB of memory. Now I am saying 32-bit because I am assuming that we are talking about a 32-bit system where the address bus is basically 32 bits in size. Okay. Now what does that mean? It means that I have process A which thinks that it owns 4 GB of memory. Process B also seems to think that it owns 4 GB of memory, right? Now that obviously cannot happen at the same time, because the total amount of memory in my system may not even be 4 GB, it might only be 1 GB, right? So how exactly does this work, right? What happens over here is, when any of the processes try to access a particular location, let's say that they are trying to access an array which is stored somewhere in the data segment out here, right? They use the virtual address, right? The address that they believe is the address of that particular variable. When you, in a C program, if you try printing out the value of a pointer, right, not star p but directly the value of p itself, right? If I try printing it out in hex, I'll get a number which looks somewhere, it's a 32-bit number, for example. Okay. Now that is just a location in the virtual address corresponding to this process. What happens is that virtual address goes through something called the memory management unit, which does something called address translation. And by doing that address translation, it converts it into something which is an actual physical address, right? Which means that if I am, let's say, trying to access something in the heap, I have done some malloc in process A and I am trying to access data which is present over there, what will ultimately happen is I will go through the MMU and it will redirect me to this set of physical address locations. It will, in other words, fetch the data from somewhere here. My process doesn't know, right? It doesn't care where exactly this physical memory is stored over here, as long as every time it tries accessing that particular element, process A and the data comes back from this location. Now what about process B? Let's say that it has also done a malloc and tries to access something which is in its heap, the same address as what was used by A, right? What will end up happening is, it will have to go look, well, I have not got process B's heap over here, right? But it would be somewhere else in the physical RAM, right? And that is where it would need to go pick up the data and then get it back. In other words, there is no way that process B can get access to this location at all. That is essentially what we mean by isolation and protection. Each process ends up being completely isolated from the others and protected from the others. Okay, so even if process B wants to, it cannot overwrite something which is in the heap of A, right? It also means that I can relocate. The interesting thing is, as far as A was concerned, I tried accessing a particular variable, it went through memory translation and it ended up at this location. Now maybe due to various, the amount of data or the amount of memory that I had was insufficient, so I had to swap out some locations, put them into temporary storage, then maybe even just kill off a particular process and then restart it and move things around. I might find that I actually had to, the operating system might have had to take a decision that the physical memory over here needed to move to another place. Of course, probably not into another processor's data, but somewhere into free RAM. Okay. The interesting thing is, as far as process A is concerned, it still continues to access the same address. It goes through address translation and now goes and picks it up from that new location. The process is completely oblivious to the fact that the address, that physically the data has been moved to a different place. The operating system has taken care of it. The address translation is transparent to the process. The process does not even know that such a thing has happened. Okay. So, this is crucial to how modern operating systems work, right? It allows us to basically separate out these different processes and run them in such a way that they do not trample on each other and can work in isolation effectively. So, the process by which this works is something which this is sort of a lightning overview of the whole process of virtual address translation, right? But hopefully will give you a little bit of a flavor of what is going on over here, right? The details of this, in order to really fully understand it, you probably need to do a bit more of an OS level course. Okay, but roughly speaking, what is happening is every process deals with virtual addresses, which are 32-bit addresses in this case. Now, out of that, what I do is, the first thing I do is I pull out the first 12 bits, right? So, remember, going back to this, I have a virtual address somewhere out here in the heap of A. I take the first 12 bits of that, and from that I basically look in something called the level 1 table. Now, this is 12 bits, 2 to the power of 12 is 4096. Therefore, what I have is, there will be 4096 entries in this level 1 table. Okay, and each of these essentially points to a level 2 table. It does not point to a physical location in memory. Okay, now the level 2 table is much smaller, right? That basically corresponds to an 8-bit value, the L2 index, right? Which basically tells me that now there are 256 entries which contain what are called page table entries. Okay, now the page table entry is actually giving me something called the physical frame number. That physical frame number is the actual sort of block address on the physical RAM side. Okay, now once I have this physical frame number, which is a full 20-bit number, see, I remember that I took 12 bits from here and 8 bits from here, right? It basically gives me a 20-bit number from this side. I take the remaining 12 bits that I did not use so far, append them to the 12 bits that I got from the physical frame number, and now this actually gives me a physical address, which is directly something that I can access in RAM. Okay, all of this happens automatically. The memory management unit walks the table. We call it a page table walk, right? So the page table walk basically says, okay, I asked for an address here, take the first 12 bits, go look up table 1, from there go find out table 2, in table 2 go look up based on the next 8 bits, get a physical frame number. Okay, now the interesting thing is, I have got a physical frame number out here because of this combination of the level 1 table as well as the level 2 table, right? This MMU has something more to it, which basically says that for each process that is present over here, the kernel can basically load in a separate sort of base address, which means that this level 1 table that I am talking about over here can give me different entries corresponding to each process, or to corresponding to each process that I have, which means ultimately that a given physical frame would be present in one of the different page table entries that I have. More importantly, what it tells me is, I might have 2 to the power of 32 locations out here. Not all of them will actually have valid entries at this point. So if I go through, pick this up, I might find that it points to something invalid in the level 2. This basically does not give me a physical frame number at all, right? At that point, what I get is what we see as a segmentation violation, right? Basically, it's a, I'm trying to access memory that I'm not allowed to. Okay, it has not been allocated for my process. It is outside the range of what is valid for my process, and therefore the system is not going to permit that. Okay, so the page table entry basically takes care of a lot of things. It gives me the actual physical frame number, but it also checks various things such as, for example, the permissions. Am I allowed to read from this particular location in memory? Am I allowed to write to it? And am I allowed to execute code that is present in this block of memory? In other words, can I perform a branch into this memory and start executing whatever data is there by interpreting them as instructions? This is a good way of sort of preventing people from just randomly jumping into the middle of an array and trying to run code. Okay. It can also, for example, have information such as whether it's user space code or kernel code, right? Even whether the data is present or not in the first place, and also certain attributes such as should the memory be cached or not. Right? So a lot of things of that sort can be present in the page table entry. So the point of this entire process is that this memory management unit takes care of this translation automatically. Each process gets its own translation table, right, which means that effectively what is going to happen over there is that if I access the same memory address in process A and process B, they will get translated into different physical addresses, or one of them may not even get translated, it may just sort of report an invalid address, right, so that I can be sure that process A and process B are never going to end up overwriting the same physical memory or even reading from the same physical memory. Now there are ways of explicitly saying that I want to share memory between two processes, but that's a separate story, we are not getting into that right now. The default is that they should be protected from each other. Okay. So this idea of the memory management unit is a crucial step, right? It is what allows us to do this kind of address translation and by extension implement virtual memory. So without having the memory management unit in place, it's not really possible to implement any reasonable kind of memory protection. Okay. So the ARM page tables for 32-bit architectures at least look something like this, right? A virtual address has the first 12 bits are used in order to get a level 1 index, the next 8 bits are used to get a level 2 index, and the last 12 bits are not used as an index, they are just basically used as an offset within the physical frame. So the combination of these first two is used in order to get a physical frame number, right? The physical frame number is also a 20-bit value. So in other words, I am taking 20 bits from here and I am getting another 20 bits as the output. Okay. So it sort of replaces the top 20 bits of your virtual address with an actual physical frame number. It also has things like the permission flags and caching attributes. All this is part of the ARM page tables. Most processors have similar kinds of MMUs, but some may have different capabilities as well.